Hi folks, welcome to class. We've got a lot to cover today, so we're gonna jump right in and get started. If you have any questions, then we can take a look at that at the end of class. But let's kind of jump right in. All the notes should be under chapter 7 in Canvas. And so we're going to start with 7.1, part 1, and then we're going to move on to 7.1, part 2.
Question.
Yes, sir.
What happened to the chapter 6 homework on Pearson? Last night I was doing it and then all of a sudden it just disappeared.
I unassigned it. So you only need to do homework for chapter 7.
Okay, thank you.
You're welcome. All right, I'm gonna go ahead and share my screen. All righty. So let's get started. All right, so in the first part of 7.1, we're going to do a quick review on some of the fundamental identities, and that includes the Pythagorean identities that is talked about in your textbook in 7.1. I wanted to throw some of the more foundational ones in there as well, just so we kind of get a good review of that. And then we're actually going to start practicing proving identities right away. Your textbook saves it for a different section, but I like to sort of integrate it along, just kind of like I did the applications for the exponentials and the logs, okay? So we're going to go through a list of fundamental trig identities, and I would encourage you to not only know them, but also love them, okay? They're very, very useful in a lot of math that is to come. And I'll try and point out which ones tend to get used in Calc 1 and which ones tend to get used in Calc 2, just so you kind of have an idea of like how far down the road you might see until you see them again, okay? All right, so we're going to start with our reciprocal identities. And we actually talked about this a little bit yesterday when we talked about chapter 6. So what is the reciprocal function for sine?
Cosine?
It's not cosine.
Cosecant?
Secant, yeah, pretty similar, but it's cosecant, okay? So one way of writing sine is you can actually write it as 1 over cosecant. And what that means is we can also write cosecant as 1 over sine theta. And so sometimes one form is more useful than another. And so it's important to know different ways that we can rewrite certain trig functions. Now, similarly, cosine and its reciprocal function secant, we can write cosine as 1 over secant theta, and we can write secant as 1 over cosine theta, right? And for our last pair, we have tangent. We can write that as 1 over cotangent, because tangent and cotangent are reciprocal identities. And then we can write cotangent as 1 over tangent theta, okay? As we think about things that tend to come up more, I wouldn't say there's a significant difference, like don't even remember the other way, but usually we take these three. So if we see a cosecant or a secant or a cotangent, one strategy as we get to verifying identities that I like to use is rewriting things in terms of sine and cosine and tangent. So that means if I saw a cosecant, I might replace it with 1 over sine. If I saw secant, I might replace it as 1 over cosine. And if I saw cotangent, I might replace it as 1 over tangent. That doesn't mean that you never use the other ones, okay? But I think in thinking about math as a whole, we tend to use the ones on the right a little bit more than on the left, but I would say they're both equally important. Okay? So those are our reciprocal identities. Next up, we have something called quotient identities. All right. And quotient identities are similar to reciprocal identities in the sense that sometimes they're so foundational that we forget that it's actually a thing. So for example, yesterday we learned that tangent was sine over cosine. And so that is actually our quotient identity. If we see tangent, we could rewrite it as sine over cosine. Now, what does that mean we could write cotangent as?
Cosine over sine.
Cosine over sine, perfect. Okay, so if you see cotangent, one way you could rewrite it is 1 over tangent, but another way you could write it is cosine over sine, okay? Same thing with tangent, you could write it as sine over cosine, or you could write it as 1 over cotangent. So there's a lot of different ways to write these trig functions, and when we get to the proving identities, I think the best thing to do is have a list of all of these identities so you kind of know, all right, does it look like this? Does it look like this? And it's really honing in on that decision making, okay? All right, we've got some odd even identities. I would say that these come up less frequently than the other ones that we've seen so far, but I did want to show them to you just in case they come up for you in the future, okay? And we're actually going to start with the 2 functions that are even, okay? Anybody know which trig function is even out of the 6 on the list?
Cosine and secant?
You got it. So cosine is even and secant is even. And so what that means is cosine of negative theta is actually equal to cosine of regular theta, all right? And secant of negative theta is equal to secant of regular theta. The other 4 are odd functions. So sine is an odd function, cosecant is an odd function, tangent is an odd function, cotangent is an odd function. And what that means is that sine of negative theta gives you negative sine theta. And same thing for the other 4. It's going to equal the negative of the regular angle. So negative cosecant theta, negative cotangent theta, negative tangent theta. Okay, so we've got some even identities, some odd identities, but again, it just gives us another way to write a certain function. So if you see a trig function that you're working with and it's got a negative in the angle, using one of these identities is probably a really good strategy, okay? All right, the cofunction identities. I think your textbook does these in 7.2, but I kind of put them here just because they're all in that same list of sort of fundamental trig identities, all right? So the cofunction means that when you see the 2 trig functions that sound very similar, except one of them has a co in front of it, that's what we mean by cofunction. So for example, sine and cosine are co-functions, all right? Secant and cosecant are co-functions. Tangent and cotangent are co-functions. And this should say pi over 2 minus theta. Sorry. So here's what's important about cofunctions. If you have a calculator handy, okay, and if you don't, that's okay. But if you have a calculator and you type in sine of 20 degrees, you get about 0.342. Okay. What is pi over 2 in degrees?
90.
90. So if we use our calculator to find cosine of 90 minus 20, let's see what we get. Cosine of 90 minus 20. Oh, shoot. It gives us the same thing. So when we say sine of 20, it is the equivalent of saying cosine of 70. If we say cosine of 20, what is that the same as?
Would it be 90 plus 20?
Let's see. So if I have cosine of 20, that should equal sine of 90 minus 20, or we could say 70. Okay, so another thing to think about when they say cofunctions, you can also think about complementary angles, angles that add up to 90 degrees. If your two angles equal 90 degrees when you add them, then the sine of one of them will equal the cosine of the other one, cofunctions. So when we fill in our chart here, we can say that sine of pi over 2 minus theta is equivalent to cosine of theta. Okay, that's like saying sine of 90 minus 20 equals cosine of 20. And we could say that cosine of pi over 2 minus theta is equivalent to sine of theta. And that would be like saying cosine of 90 minus 20 equals sine of 20. So every pair of cofunctions, whatever the function is and its cofunction, those are going to be equivalent when we're looking at complementary angles. So if we pair our secant and our cosecant, that means that cosecant of pi over 2 minus theta is equal to secant of theta. And that secant of pi over 2 minus theta is equal to cosecant of theta. And then for our last pair, tangent of pi over 2 minus theta is equal to cotangent theta. And cotangent of pi over 2 minus theta is equal to tangent of theta. Okay. So we've got these cofunction identities, and really they help us find the angle of the trig function of the complementary angle, the angle that adds to it to make 90 degrees. Okay. All right, so we've seen a lot of identities so far, and some of these are ones that we know super well, so well that we might have forgotten they're actually identities. And some of these, like the cofunction one, might be a little newer for us. But when we're looking at finding, proving identities, it again is going to be super useful if we have a chart in front of us that has all the different identities listed so that we can think about which one to use and why we might want to use that identity. So that brings us to the Pythagorean identities, okay? Now with the Pythagorean identities, these ones come up a lot. In fact, In my Calc 2 class earlier today, we used a bunch of Pythagorean identities. And last week in my Calc 2 class, we also used a lot of Pythagorean identities. You use the Pythagorean identities a little bit in Calc 1, not quite as much, but definitely when you get to Calc 2, you're going to be using them a lot. Okay? So let's start with what we know about the Pythagorean theorem. The Pythagorean theorem says that a squared plus b squared equals c squared. Yeah? And we're going to put that together with what we know about the unit circle. All right. So, quick review from yesterday. A unit circle has a radius of
1.
1. Beautiful. Okay. So, that means that we've got a radius of 1. And if I pick a random point on my circle and I wanted to find out the coordinate of that point, okay, how long is the pink line that I just drew if it's a unit circle?
Square root 2.
No. How long is that line? That line represents the radius of the circle.
1.
So it's going to be 1, okay? Now, from here, if I want to think about a horizontal and a vertical component, I could say that like this is going to be how tall the point is or what the y value is. And this is going to represent the x value of the point. Now, I'm going to take this triangle, blow it up a little bit. Okay. Now, we know that this side is 1 because it's the radius of the circle and it's a unit circle. What does the x value of a coordinate on the unit circle give us again?
Cosine.
Yeah, the x value is cosine. So instead of x on the bottom, I'm going to write cosine theta. And that means that sine theta represents the y value of the coordinate. And so I'm going to label this up and down side as sine theta. Now this is a right triangle. By definition of the x being horizontal and the y being vertical, they meet at a 90-degree angle. So if I were to take these 3 sides labeled as they are and plug them into the Pythagorean identity, check out what I get. Cosine theta squared plus sine theta squared equals 1 squared. And here's how we normally write trig functions that are raised to a power. We don't write them like this. Here, let me do it in red so we know not to do this. We don't write this, cosine theta squared. The way this gets read is you square theta and then you take the cosine. But that's not what we mean. We want to take the cosine first and then we want to square it. So the way we write it is we write it as cosine squared theta. We put the 2 in between the cosine and the theta so that we don't get confused which one we're doing first. So the squared in between there means find the cosine and then square it. We could do the same thing with sine. So instead of writing sine theta squared, we'll write it sine squared theta. And we all know that 1 squared is just 1. Okay? So this, my friends, is our first Pythagorean identity. Cosine squared plus sine squared equals 1. Okay? This is the only one that I memorized because there's so many other things in math to memorize that sometimes it's more helpful if you can memorize one, like this one, and then figure out how to get to the other two, okay? So that's how I'm going to explain where we get the other two from, because there are 3 Pythagorean identities, okay? This one, cosine squared plus sine squared equals 1, is one to definitely remember, okay? But from there, let's do this. I'm going to ask us to divide by cosine squared theta. Meaning, I want us to take the entire equation and divide by cosine squared, okay? So let's see what happens. Cosine squared theta divided by cosine squared theta plus sine squared theta divided by cosine squared theta equals 1 over cosine squared theta. Okay, so I took every term in the pink Pythagorean identity and I divided every single term by cosine squared. Now I want you guys to help me reduce. What does that first term become?
1 plus tan squared equals secant.
Very nice. So I think we all get cosine squared divided by cosine squared equals 1. To make it a little bit more clear, I have sine divided by cosine. That gives me tangent, and then I have to square it. That's why sine squared divided by cosine squared gives me tangent squared theta. Okay. And then, David, I'm sorry, what did you say for the third term? I forgot already.
Secant squared.
Secant squared, excellent. And how did you get that?
1 over cosine equals secant. So I guess I just kind of thought that way.
Yeah, very nice. 1 over cosine is secant, and then we square it, so it becomes secant squared. This is a second Pythagorean identity, okay? I've been teaching, let's see, my Calc 2 class started a week after you guys, and we've already used the cosine squared plus sine squared equals 1 and the 1 plus tangent squared equals secant squared more times than I can count. So in the first few weeks of Calc 2, you're going to use those two a whole lot, okay? The third one, we don't tend to use as much, but we can actually derive it using a similar reasoning that we did to get the blue Pythagorean identity, okay? So we're going to go back to the original. And this time, I'm going to say, let's divide by sine squared theta, okay? That means I'm going to have cosine squared theta divided by sine squared theta plus sine squared theta over sine squared theta equals 1 over sine squared theta. All right? Sine squared divided by sine squared is 1. That part's easy, so I'll give that to you. What does cosine squared divided by sine squared give you?
Cotangent squared.
Wonderful. And 1 over sine squared gives us?
Cosecant squared.
Good, very good. And that, my friends, is the third Pythagorean identity, okay? So for however many years that I've been learning and teaching math, I chose to memorize the one in the pink. I know that one. Anytime you ask, I could tell you that cosine squared plus sine squared equals 1. The other two, I do tend to derive that so I can kind of remember which way it is. So if you are a person who is super good at memorizing, feel free to memorize all three. But if you're someone who like worries about either memorizing it wrong or just not being as good at memorizing as someone else, memorize the one in the pink and then figure out how to get to the other two, okay? But all three of these are considered Pythagorean identities, and we use them a lot in proving identities when we have cases where we have cosine squared or cotangent squared or tangent squared, okay? So when we see squares, one thing we could replace it with is a Pythagorean identity, okay? So to kind of prime us a little bit, what could I call this? If I wanted to write sine squared theta in a different way, oh, it froze on me, hold on. Okay, sorry, now you can see it. That's sine squared theta. What is another way that I could write sine squared theta?
1 minus cosine square of theta.
Beautiful. 1 minus cosine squared theta. Good. Okay. What's another way that I could write cotangent squared?
Cosecant square theta minus 1.
Good. And we just took this one and we just subtracted the one to the other side to get the cotangent squared. Okay? And so then maybe a last good example could be, I could say tangent squared theta could be secant squared theta minus 1, okay? We don't consider those as separate identities. We just consider them as variations of the Pythagorean identity, okay? And more often than not, we're not gonna see, we'll see like sine squared in an identity and we wanna replace it with 1 minus cosine squared. Okay, or we'll see tangent squared and we can replace that with secant squared minus 1. All right, so let's get to practicing verifying identities. Now this is historically a topic that a lot of students either really enjoy or they hate it, like a lot, okay? So if you're somewhere in the middle, that's definitely on the rare side. I feel like people either really like this or they really don't. But no matter how you feel about it, I believe that you all can do this. And so as we walk through our examples, I don't want to just write out like what I'm doing. I want to talk a lot about why I'm choosing to make the decisions I make. I think what makes this hard for folks is that I can't tell you a single way to do verifying identities that works every single time. And so for some of us who really like that one formula that works for everything, you're not going to find that here, okay? And if you want to go into a lot more higher math, this is a good place to start thinking about math in a different way than it's just a formula, okay? So let's get started. All right, we've got example 1 here. We have tangent squared times 1 plus cotangent squared equals 1 over 1 minus sine squared theta, or x. So, give me some ideas. What might we want to try? Tell me one idea. And
I think the first step would be to convert the 1 minus sine to the second power into cosine to the second power, and then that would become secant squared.
Okay, so I heard a maybe let's start over here and use the Pythagorean identity. Okay, that's definitely a possibility. Who else has an idea?
Make the change the cotangent so that everything is easier to combine like terms.
What do you mean by change the cotangent?
Like cotangent would equal one second.
Okay.
So I would say that 1 plus cotangent square of x, it will be cosec is equals to cosecant square of x.
Okay, so a Pythagorean identity, but a different Pythagorean identity and on a different side. Okay. What other strategies might people want to try? These are all very valid, by the way. I'm not asking for more ideas because you guys are wrong. I'm asking for more ideas because it's important, especially for folks who don't know where to start, to hear different ideas, okay? So any other potential ideas on where we could start with this?
I would also say that you can convert everything to sine or cosine terms to be more easy to reduce that.
Okay, that's a really great strategy as well. So maybe what I think you mean by that is instead of tangent squared, you would write that as sine squared over cosine squared?
Yes, and the other, like the other functions that are there, I would convert them even to sine or cosine, even there is 1 over something.
Right, right. Okay,
Yeah.
cool. Anybody else have like a maybe we could try this? Okay. Well, one idea that hasn't been shared is sometimes I try and do something that is just straight up algebra. I sometimes try and like distribute if I see parentheses in a term out front. Okay. Now, all 4 of these methods that were brought up, and potentially others that people haven't shared, but the ones that were brought up here are all valid, okay? But here's one thing I want us to be really careful about. When we are doing proofs, we need to pick one side of the equation, one side of the identity. And we can only work with that side. And we need to make that side that we pick equal to the other side. So there's no like, bring some terms over to this side and then bring them over to the other side. There's no like cross-contamination like that. We need to take, if we pick the left side, we're going to work only with the left side and we're going to turn it into 1 over 1 minus sine squared x. Or if we choose to work with the right side, we need to get it to look like tangent squared x times 1 plus cotangent squared x. Okay? So when we're doing identities, verifying identities, no cross-contamination, you pick one side, you work with that side, you make it look like the other side. Okay? I tend to pick the left side to start with, but you don't have to. You can choose either side to start with, okay? The only way that you will know which side you like to pick is if you practice picking sides and then you figure out through experience one of them is better for you than the other. So let's start with the left-hand side here. And I like the suggestion of the Pythagorean identity since we just learned that. And so let's take our tangent squared. We'll keep that. And we're going to replace 1 plus cotangent squared. Let's go back up for a minute. 1 plus cotangent squared, I'm going to replace that with cosecant squared. Okay. Now, that we've used the Pythagorean identity, I'm going to say, let's use the other strategy of convert everything to sine and cosine, okay? And by everything, I mean the things on the left-hand side. So another way to write tangent squared is sine squared over cosine squared. And what's another way to write cosecant squared?
One over sine squared.
1 over sine squared, good. All right. Now, rules of fractions still apply. So I have a sine squared in the numerator and I have a sine squared in the denominator. They reduce to 1. So my left-hand side now looks like 1 over cosine squared x equals 1 over 1 minus sine squared x. How can we get the two sides to look exactly like each other? What do we need to do to that left-hand side?
Could you use the identity to make it 1 minus sine squared x?
You absolutely could. We're going to replace cosine squared with 1 minus sine squared, and we've done it. The left-hand side looks like the right-hand side, so we are all set to go. Okay? So, a few strategies to highlight. Pythagorean identity, if you see one, not a bad idea. Okay? Converting everything to sine and cosine, not a bad idea. And between those two, we were able to verify that this left-hand side equals the right-hand side. Now, I think one word of advice is sometimes people are like, let me change everything in one step. And then it just seems to get more and more complicated, okay? And so I would encourage you to kind of take it slowly, like change one thing and then maybe change another thing and see what happens. It's almost not as good idea to change everything all at once, because sometimes you change something that it would have been better if you kept it, but you didn't give yourself a chance to see that, okay? We ready to try a second example?
Yeah.
Yes, okay. All right, here we go. Example number 2. Let's take a look at this for a moment, give you some think time. And in about 30 seconds or so, maybe we can share out some strategies, okay? And again, you might choose to do this in a totally different way than we showcase here in this lesson. That doesn't mean you're wrong, but I think it's useful for everyone if we can kind of hear these ideas. All right, who's got some ideas? An idea and a reason.
I think the first thing you would do is convert the secant squared to 1 plus tan squared.
Okay, so maybe using a Pythagorean identity, okay? Who else sees something that we could do?
I will start for the right-hand side since it looks more complicated than the left one.
So you wanna, yeah, but what do you wanna change? Like, is there an identity that you wanna use? And if so, what is it?
Well, I would do the same thing as my classmates say, change everything to Pythagorean identities.
Okay. So Pythagorean. Anybody have a different
Could you change
I would probably turn the secant squared and cosecant squared into fractions.
So turning them into sine and cosine?
Yeah.
Okay. So we could do Pythagorean. Maybe we could convert into sine and cosine. Okay. Any other ideas?
Could we change tangent and cotangent?
The numerators on the left-hand side?
Yes.
And you turn those into sine and cosine?
Yeah, so like sine over cosine minus cosine over sine.
Yeah, for sure. Okay. So it sounds like we've got some ideas. I think we could pick any one of those and it would be totally fine. Okay. Let's go ahead and convert the left-hand side actually and kind of see where that takes us. Okay. So this idea of sine over cosine, we could take the tangent and make it sine x over cosine x. So tangent became sine x over cosine x minus cosine x over sine x, and that was my cotangent. Okay. So I still have tangent minus cotangent on the top, but I just wrote it differently. And then in the denominator, I have sine x cosine x. And I hope I can make that equal the other side. Part of what helps me make decisions is keeping in mind where I want to go. So I see two fractions on the top, and sometimes we're going to see two fractions and we want to make them one fraction. And sometimes we see two fractions and we want to keep it as two fractions. So how do we know when? And to answer that question, I look at the other side. And I notice on the other side, there are two fractions, secant squared and cosecant squared. So what I'm going to do is I'm going to split this into two fractions, okay? Sine x over cosine x over sine x cosine x. That's the first fraction. Minus cosine x over sine x over sine x cosine x. So I've got my tangent over sine x cosine x, and I've got my cotangent over sine x cosine x. And again, my reason for splitting them is because I wanted to make it into two terms like I have on the right-hand side. Now, these fractions in a fraction, we're just going to rewrite this. So we're going to end up with sine x over sine x cosine squared x for the first fraction. And the second fraction is going to become cosine x over sine squared x cosine x. And I hope that that equals secant squared x minus cosecant squared x. And if you're wondering where the tangent went, it's the sine over one of these cosines. And the cotangent is this cosine over one of the sines, okay? Now, from here, reduce, and look what we get. 1 over cosine squared minus 1 over sine squared equals, we hope, secant squared minus cosecant squared. And if we use our reciprocal identities, the reciprocal of cosine is secant, The reciprocal of sine is cosecant. And we have verified this identity because both sides are equivalent to the same thing. Okay? Now, if you chose to start with the right-hand side, you should still be able to get back to the left-hand side. You might just need to do some different steps, depending on whether you decide to use Pythagorean or you decide to convert into sine and cosine. It will just take a different step, and at the end, you won't be splitting fractions, but you'll be combining fractions, okay? And I thought someone brought up a really great point earlier, which was, oh, I'm gonna work with the right-hand side because the left-hand side looks more complicated. And I actually wanna challenge us to flip that notion a little bit, because I tend to pick the more complicated side so that I can make it less complicated. Sometimes it can be a little tricky to make a less complicated side into a more complicated version. Okay, so sometimes it's actually better to work with the more complicated side. All right, let's take a look at example number 3. I'll give you about 30 seconds. Think about some ideas. What do you want to do? All right, what ideas do we have out there for example number 3?
I would start with the right-hand side because it's more complicated.
Okay, and what would you do to that right-hand side?
Can I split the fraction or the division?
You can. You mean write it like 1 over cosine plus sine over cosine?
Yes.
Yeah, you could do that. So let's see. Okay. Now what do you want to do?
Convert sine x divided by cosine x to tangent.
Okay. Now what?
So 1 over cosine of x, that is secant x.
Mm-hmm.
And then if I work with the left-hand side, I will have cosine of
Can't
x.
do that. You can't work halfway with one side and then switch to the other side.
Okay.
Okay, you got to work with, if you pick one side, you got to work with that whole side the whole time.
Okay, I cannot switch right and forth.
Oh, nope. Yeah, so if you think about like a good friendship, you guys meet in the middle a lot. You compromise, right? Or like a good relationship, you compromise. Mathematicians don't like that. We're a very special breed of people, and we want to only work with that one side, my way or the highway kind of situation, okay? So that's why we're not trying to work with both sides. We want to pick one. We want to go with that one side, okay? Now, I think you made very valid substitutions here. Everything you did was mathematically correct. But as we keep reminding ourselves of what we're trying to make it look like, it's not getting closer to that, okay? And so for that reason, I might not use the method of splitting fractions here. So I don't want to erase this because I think it's good thinking, but I'm going to shrink it a little bit just so we kind of have it here to look at, all right? But I think that in this case, It's okay to try something and then realize, ooh, this is not going the way I want it to. Anybody else have any ideas? Okay. Well, let's try doing this one working with the right-hand side, since we've seen a few examples where we work only with the left-hand side. So I want to show you you could work with either side, okay? But I'm going to start by writing down the left-hand side, and then instead of splitting the right-hand side, I'm going to say, I want to multiply the right-hand side by 1. Is that valid? Can I multiply something by 1 in an equation?
Yes.
Yeah, I can multiply by 1. Now I can be really creative about how I multiply by 1. I could say 1 over 1. That would be fine. But I could also do 2 over 2. That would also be fine. Or I could do pi over pi. Like, there's nothing wrong with that. But I don't think any of the versions I've listed are actually going to be helpful here. So instead, what I'm going to multiply by is 1 minus sine x and 1 minus sine x. And where did I come up with that from? Because I looked at what was on the other side, and I was like, if I had a 1 minus sine x in the denominator, I would be well on my way to making the two sides look the same. So let's see what happens. Cosine x over 1 minus sine x equals cosine x times 1 minus sine x in this denominator. And I want to FOIL the top. So 1 times 1 will give me 1. And then the outers and the inners, it's sine x minus sine x, so that gives me 0. And then my last terms give me minus sine squared x. Okay. Now you might be asking me, why would you FOIL the top and not the bottom? Like, why didn't you distribute that cosine? It's so easy. You just do cosine minus cosine sine. Well, here's why. I looked ahead to what I want, and I want to have that 1 minus sine x on the bottom. So if I distribute that cosine, I might forget that I actually have the 1 minus sine x on the bottom already. So I'm going to keep it out and not distribute it. What's another way I can write the numerator?
Cosine squared of x.
Beautiful. All right. This is another reason why I didn't distribute that cosine. If I don't distribute it, I can reduce. If I do distribute it, I might not realize I can reduce. And what does that give us? The left-hand side equals the right-hand side. Okay. So this strategy here, multiplying by a fancy way of saying 1, is a new strategy I want us to consider as we go through things, okay? So you could convert things to sine and cosine, you can use Pythagorean identities, and sometimes you can multiply in a fancy way of saying 1 so that you make a Pythagorean identity come out, and then you can use that Pythagorean identity, okay? Any questions on number 3?
I actually have one.
Okay, what's up?
So you can't. So at the beginning, you can't cross out the cosine x and the cosine x because they're the same and it's a proportion.
No, you can't. For a number of reasons. They don't cancel each other out because they're on different sides of the equal sign, and you can't work with both sides. You have to pick one and go with it.
Gotcha.
Okay? All right. Let's try another one. So if you're looking at all of these examples being like, why is every example so different? I picked that on purpose. Okay, I picked cases that I thought were highlighted some of the most common strategies that we use so that we could see not just that they use different strategies, but also talk and listen to why we might need different strategies. Okay, so for example 4, we're going to look at the left-hand side, okay? And here's why. If you think back to, I don't know, middle school, you learn that a squared minus b squared factors, and it factors into a plus b times a minus b. Yeah? But depending on your future math teachers, you may or may not realize that pattern actually happens for every even powers that you have. So what I mean by that is a to the 4th minus b to the 4th can factor into a squared plus b squared times a squared minus b squared. What does this factor into?
Would it be sine squared theta plus cosine squared theta times sine squared theta minus cosine squared theta?
Oh, sorry, I was asking about this. A to the 10th minus b to the 10th.
Oh, sorry.
That's okay. I got you for that next step, though. We'll write it down in a little bit. But folks, what does a to the 10th minus b to the 10th factor into?
A to the 5th plus b to the 5th times a to the 5th minus b to the 5th.
Very nice. Okay, so this difference of squares, the reason why your middle school teachers were like, you need to know this, is because it's actually the beginning of a much larger pattern, okay? Now, Veronica already jumped ahead to that question, and so we're going to be able to apply that middle one to the sine to the 4th minus cosine to the 4th. So let me just write down what she wrote, what she said, sine squared plus cosine squared. And then you said sine squared minus cosine squared. And that's going to equal, hopefully, the right-hand side. All right, when we factor this, we are able to make this left-hand side way simpler right away. What can we substitute here?
The 1 sine square of theta plus cosine square of theta is equal to 1.
Beautiful. You use the Pythagorean identity, that goes to 1, and then you just have this. Sine squared theta minus cosine squared theta equals, hopefully, that right-hand side. All right. We're going to keep the sine squared, okay? We're going to keep this sine squared because in looking at the other side, we have a 2 sine squared. And instead, what we're going to try and do is say, how else can I rewrite cosine squared? So instead of cosine squared, I'm going to write that as 1 minus sine squared. I'm going to use the Pythagorean identity, but I just solved for cosine squared. And now when I distribute that minus and I distribute that minus, I'm going to get 2 sine squared theta minus 1 equals, oh, perfect. It equals the right-hand side of my equation. Okay? So sometimes factoring actually helps you turn one side into the other side. Okay? So that's just another strategy to add to our toolbox. All right, let's see, we have 5 and 6. All right. We're actually going to pause here. We're going to take a short break. And when we come back, we're going to finish this section, and then we are going to start the second half of 7.1, okay? So I'm going to stop sharing my screen for a second.